So today is going to be the last lecture on optimization, and I'm going to spend pretty much all the time on these two things: constrained optimization, all of these are nonlinear optimization. I'll first talk about why nonlinear optimization makes things hard. What makes it difficult. Talk about two kinds of nonlinear optimization. Again, this is a very large field. There are many, many things going on, and I can't discuss everything. I'm just going to give you a sort of taste of things. One is constrained optimization, where we have essentially mathematically nice functions that are continuous, twice differentiable, and defined over the entire domain. In this case, R to the n, the entire real hyperspace, and that makes things nice. And then we can use two kinds of techniques: the Lagrangian, or what I call KKT or Karush-Kuhn-Tucker conditions. So talk about these two. And then when we don't have something that's nice, which is actually most of the real world, then we have to use heuristic optimization. And the most successful one of these actually is hill climbing. This turns out to be something that works almost all the time. I'll talk about hill climbing in some detail, some variants of hill climbing, and then give you just a brief outline of genetic algorithms. There are many, many other heuristic algorithms out there, probably 10, 20 more that I want to just mention, but I won't get into in any detail. But we'll start again with the first thing, which is just nonlinear optimization. So why is nonlinear optimization hard? And let me try and give you an intuitive understanding of why linear optimization is easy. So in linear optimization, generally speaking, we have some function, y equals fx, okay, and these are vectors. This is the objective function. Maybe I should just call it O equals fx. And the nice thing is that because f is linear, okay, a small change in a component of x causes a small change in the optimal value over here in the objective function. So if I think about the polytope that we discussed, in linear programming, there's some kind of hyperdimensional thing. As I walk along some edge of this polytope, all right, essentially what I'm doing is when I walk along the edge is to change some number of elements of this vector, by small increments. And as I walk along it, what's happening is that the objective function is also going to increase linearly. So as I walk along this, the objective function goes smoothly, linearly, which means it always increases or decreases. Okay, that's basically it. It's linear. There's not a whole lot of stuff going on. It's some combination of a1, whatever, x1 plus a2, x2, etc. So if I change some number of these an's in some fashion, which is just a vector along this hyper edge, the output is going to be changing by some small increment. It's not going to change its sign. It's not going to go up, down. It's either going to keep going up or keep going down, which means that we run out of room in some sense at the edge of the polytope, at the vertex, and that becomes a candidate for an optimal point. And if that's not the optimal point, we find some other edge, kind of move along that part, and we come to the edge over here. So linearity allows us to do this hopping from vertex to vertex of the polytope in the case of linear programming. Of course, in the case of integer linear programming, we can't do that because, again, we have to make jumps. We can't go here. We have to go from here to here to here. And when you make these jumps, of course, things go crazy because the objective function can change. Similar problem arises with nonlinear optimization, where what happens is that when you have some kind of hyper edge, if you want to think of it that way, as we move along, actually what will happen is that the objective function can go up and it can go down. It can go up and down many times, okay, depending on how it's defined. And so we don't have this nice property that the optimal value lies at a vertex of the polytope, okay. It can be anywhere, okay. So we're kind of stuck. And this fundamentally is the reason why we can't just use linear programming for nonlinear systems. Nonlinear systems tend to have a completely different type of approach altogether. So let me give you sort of intuitively one approach that we know how it works. We've done this probably in high school calculus, and that's to find the maximum of some function of one variable. So I have some function for x, I have fx, And the optimization problem here is, I have some function defined in some fashion, and I want to find the minimum or the maximum value, right? This is a classic problem in real analysis. What do? We basically take the derivative of fx. If f dash x is defined, we set f dash x equals 0, and that gives us all the points where the slope is not changing. And Fermat's theorem tells us that these points, including this one here, all the points where the slope is 0 are the candidate values for the minima or the maxima of this function. And then we take the second derivative, and that tells us whether it's actually a minimum or a maximum. So this is sort of straightforward elementary calculus. So can we use this technique? Can we use this approach from calculus to find the maximum value? Why not, right? So in the first class of techniques, what we do is to generalize from the classic real analysis to what's called Lagrangian optimization. And so Lagrangian optimization, so let me so in Lagrangian optimization, what we have is some function f that we want to find you want to find the value of x such that fx is maximized. So find given fx, find x star such that fx is maximized. Now, if that was all that we had to do, we would just use Fermat's theorem. We would just assuming that f is twice differentiable and continuous, right? We need those two things, so f is mathematically nice. If it's twice differentiable continuous over the domain, then we just finding this is easy, right? We just do it, we plug and chug. But we want to do, Lagrangian says given fx and constraint gx, okay? So these are again vectors. Find x star such that fx is maximized subject to gx equals c. So gx is then the constraint that says you must have gx equals c while simultaneously trying to maximize fx. Okay, so this is where it becomes a little bit more interesting. If you're not giving the constraint, then it's just straightforward. It's just real analysis. It's no big deal. So what I'm going to consider now, and this is the basis, as I said, of Lagrangian optimization, is given fx and a constraint gx, find the value of x star such that fx is maximized and gx is equal to c. Okay, so any questions about the setup over here? Now it turns out that this type of constraint function and this type of function is very, very common in game theory. So when you study game theory, pretty much every game will be cast in the form of find the value of x such that this f is nice, okay, mathematically nice, subject to this, and pretty much all the theorems in game theory fall out of this pretty naturally. So it's a useful thing to have again in your tool belt as you start approaching these kinds of problems. So how do we solve this? And there are kind of two approaches to doing it. One approach of doing it is sort of a cookbook formula, which I'll come to. But before I get to the cookbook formula, I want to tell you the intuitive understanding of how it works. Then I'll show you the cookbook formula, and then we'll do an example, with the cookbook to show you how that works. So we'll start with just a two-dimensional case, just because it's easier. And so in this two-dimensional case, we have some function f, x, y, and g of x, y. And we want to find the values of x and y. Again, now x and y become scalars, and g, x, y equals c is my constraint. Okay, that's my constraint over there. Okay. Now, the technique, the thing you need to remember now is a notion called a contour or a level set. And a level set, to go back to this picture over here, I sort of draw a line like this, and then I have these 2 points. These 2 points have the same value of fx. So it's called a level set for that level. Here is another level set. Here's a level set with 4 elements, and so on. I can kind of draw these level sets over here by drawing these lines, and that's why it's a level set. As the level rises, I have different level sets. Now, this is a one-dimensional case. In two-dimensional case, generally speaking, what you have is a contour. So what is a contour? A contour is you have some kind of G is defined over X and Y. So we can think of G as being a surface, right? And what would, like a hill, right? We have a hill, some shape, and we draw these planes that are parallel to the ground. And as we do that, what we get is we get these contours. So, you get the contours which are layered one on top of the other. And if you've seen a topographical map of a region, you understand exactly what's going on. These are the contours of some surface that are drawn over here, where the surface is something, and I'm kind of slowly raising up the level, and I get these continuous curves. Okay, now in general it won't be continuous, but for these nice functions we're going to get these continuous contours. Okay, so any questions about that? All right. So this is like if you're cooking, this is like slicing a potato. So each time you slice a potato, you can think of them as being level sets or contours. It's a nice way to explain it to somebody who's not mathematically oriented. So this is just slicing potatoes, or in this case, a kind of funny vegetable. At any rate, gxy equals c is nothing more than a specific contour, like so, right? It's just got to be some contour like this, and that's gxy equals c. So no big deal, that's just a contour. So what the constraint tells us is that we are forced to walk along that contour. We cannot go above or below on this particular hill. We're going to have to stay on that level set. Imagine a road going around the edge of the hill, and you have to only go along that road. Okay. Now what we'll do is we'll start looking at f. Okay. In the same way as G is defined on the entire plane, I said it's continuous, twice differentiable on the entire plane. F is also continuous, twice differentiable on the entire plane. And just like G has its contours, F has its own contours. F's contours may be quite different. F contours may look like this. For example, just to kind of pick something. And what happens when I overlay this F contour on the G contour, right? What happens is that if I just consider this one over here, it's going to intersect F's contours. So maybe I should use a different color here. So let me use the green. And so I'm going to get these intersections with F contours over here. I'm just drawing parts of the contours, okay, but they just intersect these different contours of F, okay. So some contours of F are lower and some are higher, okay. For example, this is a lower contour, this is a higher contour. So as you walk along G, you're going to kind of intersect with the lower and higher contours. What's going to happen is that each contour corresponds to a specific value of F. Okay, so as you go along the G contour, the value of F is either going up or it's going down, right, compared to the previous value of F. So as you keep walking along, essentially what will happen is at each step you say, what's the value of F? Has it gone up or has it gone down? Has it gone up or gone down? You keep doing that, and what will happen is that at each step you're going to have an answer. Yes, it's gone up or it's gone down. Now, the point at which you want to stop is when you were first going up and now you're going down, right? You first go up and you go down, exactly like over here. So if you imagine now that we have decided already that G is the contour of G, and this is the set of values of F we find, okay? Exactly this over here. Well, what we want to do simply is to find those stationary points along F, where it's become a one-dimensional problem in some sense. But I really have to find only those points of F where I'm going up and then I start going down, and this becomes those points where the constrained value of F is maximized. Okay, so if you look at those values, what will happen is that you're going to actually barely touch some kind of, and it's not going to intersect anymore, it's going to barely touch, like so, some extremal value of F. So if this were extremal value, it's just where you just touch that highest value of F, then everywhere else it's going to be lower. So that's your maximal value. So we're looking essentially, and this is where I'm getting, trying to motivate you, is those points where the contour of G and the contour of F are going to be tangential to each other. Okay? If you imagine overlaying this with this and we constrain ourselves, we want to find that point where the highest value of F is just tangential to this contour of G. And if you do that, what will happen is that the gradient of f and the gradient of G are going to match each other. Okay, not necessarily in sign. So what's a gradient? Probably should define that. So gradient is basically defined as this. Gradient of G is del of Gx is just sort of partial del by del Gxy is del by del x, del by del y, and you can think of it as a vector that's perpendicular to contour. Okay, this is just the partial derivative with respect to x and y. The partial derivative with respect to x tells you the slope with respect to x, and the partial derivative with respect to y tells you the slope with respect to y. If you take the vector of these two slopes, that's called the gradient, and basically you can think of it as a vector perpendicular to the contour. Now what we're saying over here is that tangential, by definition over here, just means that the two gradients are aligned. So we can say that del G and del F xy, okay, are the same. But it's not exactly the same. What we're going to basically say, we put a lambda over here. So lambda times del Gxy is del Fxy. So these two gradients are in the same direction, but they may be in opposite directions, and they may have different ratios because the slopes may be different. But at least we know for a fact that it's just a scalar multiplier. They're not pointing in different directions. Okay, so tangentiality just means that these two slope lines share the same gradient. It could be tangential sort of inwards, like so, in which case they'll have the same, or tangential outwards, in which case they'll have opposite signs, and the absolute value may also change, but we get this over here. Del Fxy is lambda del Gy. Okay, so let me pause for a minute. Does this make sense? Right? So I'm trying to intuitively show you that as you walk along G's contours, we want to find the point where it's tangential to the highest F contour, and that tangential point by definition is where the two gradients match, and so mathematically represented as just saying that this gradient and this gradient are scalar multiple of each other, where lambda can be positive or negative, and so we have sort of a mathematical
Is there always a tangential point?
Is there always a tangential point? Yeah. Again, when you have these things, when the functions are mathematically nice, right? Then we are going to be tangential to some contour of f, because the contours are all infinitesimal anyway, right? It's not like we have integer constraints or anything like that. So infinitesimal contours. It's going to be tangential to some contour of f, and we want to find just that one point, because that is the point at which f is maximized subject to g. Yes?
Why actually, when the tangents are same, why is f is maximized?
Why is f maximized? Okay, let's go back to here. As we walk along the g contour, it's true, it has to be the case that f has some value there. Doesn't matter what it is. Let's say the value of x is d1, right? That's some value of d1, right? Now I step a little bit along the contour. Now the value of f is d2. Now what I'm saying here is that the contour, initial contour value for this was d1, and this was on the d2 contour. So I'm going up on the f hill from the d1 contour to d2 contour, or I'm going down on the d hill from d1 contour to d2 contour, right? If I draw this as d1 and I call this d2, for example, if that d1 intersects over here, and this d2 intersects over here, as I go from here to here, I'm actually dropping down on the f hill, right? So as I go up this contour level set, I'm going to go up and down the f hill, just like I'm going up and down over here. I want to find that contour of f such that, I'm not going up anymore. After that, it's all downhill. Okay, and that, of course, is going to be the maximum point of f subject to g. Now, the actual maximum point of f may be over here, right? But subject to g, the highest point may be over here. Maybe this is d3, and then what's going to happen is d3 is the one that is just barely touching over here. Any other questions over here? Okay, so that's why I said, you rode down the hill. As you go on this hill, that's a g hill, you keep evaluating a value of f, okay? And the point at which f attains its maximum is going to be the point at which on f's contour and g's contour you have the same gradient. Okay. So that is sort of the intuitive understanding, and to get this, you have to think about it a little bit more and probably remember your freshman calculus. I hope you studied a little bit of multivariate calculus, but if you remember that, or at least you just remember that the vectors are perpendicular to the contour, a little bit of thought should show you that in fact you're going to have the perpendicularity. So if we have this, now we can define what's called an auxiliary function. So now we're going to change from intuition to plug and chug. The plug and chug says we're going to define an auxiliary function f, and the f is defined to be nothing more than f x y. So f is a function of x and y as well, plus lambda g x y minus c. Okay, that's the auxiliary function. And what we do is that we're going to look at the stationary points of fxy with respect to, I should actually, let me write this properly. This is not fxy, it's fxy lambda. Okay. Now, let me just kind of explain what's going on with this fxy over here. This auxiliary function, in sort of, again, to use the cookbook approach, says take the function you want to maximize, add to it lambda times the constraint like this. Okay. And if you do this, and actually you can do this for multiple constraints, there's no limit. You can have 10 constraints. You just say lambda 1 times this plus lambda 2 times this, etc. We can just keep adding them as we wish. Now, what we're going to do is we're going to find the maximum or the stationary points of f with respect to x, y, and lambda by setting the partial derivatives with respect to x, y, and lambda to 0. All right? Okay. Why are we doing this? Well, if you look at this carefully, you find that the partial derivative of this, okay, with respect to x and y are basically going to give you the points where the partial derivatives of, where the gradient of fxy, okay, by setting it to 0, the gradient of fxy and the gradient of gxy minus c are going to basically be aligned with each other, because the partial derivative of c, of course, is 0. So when these two align with each other, what we're going to get is that we're going to get lambda del gxy equals del fxy, right? So in this function, just by setting the partial derivative of x and y to 0, we get the tangential points. And then when we set partial derivative of this to, or with respect to lambda to 0, we get the constraint gxy equals c, and that comes out right away. So both the tangential points and both the tangential points over here as well as the constraint all drop out automatically by just setting the f xy lambda to 0. So just to kind of show that over here, let's just look at this. So basically partial x, or maybe I should just, if I define the gradient to be, just look at the gradient with respect to x, y, ignoring lambda, basically this is going to be gradient x, y, f minus lambda gradient x, y, g, okay? And we know that this is what you want to set to 0 because there's the tangential points. And so by just setting gradient f to 0, we get the tangential points. And then if you just take the partial del lambda f, this is basically nothing more than the g x y minus c. And if we set that to 0, so if you set this to 0, we are going to get, is it a plus or a minus? Okay, plus, it doesn't matter. Lambdas can be negative. So if you do this, we get the two gradients to align. And if we do this, we get the constraint. So this one single auxiliary function, f, x, y, lambda, allows us to get both the tangential points as well as the constraint in one shot. And that's why the auxiliary function is nice. And the nice thing is it generalizes as well. We can add to it lambda gxy, lambda 2, g2xy, lambda 3, etc. Keep adding that as you want. And when you set the partial with respect to lambda 1, lambda 2, lambda 3, lambda 4, each of those constraints will be automatically be given to you as well. So this Lagrangian multiplier approach kind of works. So this is called the Lagrangian multiplier. And then so it was invented by Lagrange, as you can imagine. Okay. So let me try and summarize the Cookbook approach. We start with the function f. Now it has to be twice differentiable, continuous, and unbounded over the domain, so there are no edge points. Similarly, g is a nice function, and the constraint is gxy equals c. We define the auxiliary function over here, which is fxy plus lambda gxy minus c, and we set the partial derivatives with respect to x, y, and lambda to 0, and that gives us 3 equations. Okay, we solve the 3 equations simultaneously, and then that gives us the stationary points of capital F. Now these stationary points can be maxima or minima. Constraint maxima, constraint minima. So we take the second derivative, and that tells us whether it's a maximum or minimum. So we have to do that over here. And the reason why you can do all this nicely is because f and g are both twice differentiable. So clearly capital F is also twice differentiable, and that allows us to compute the constrained optima of this function over here. Okay. So any questions? And then I'll do an. Oh, it's already this late. Okay. So any questions? After we'll take a break, and then I'll do an example illustrating this in more detail. Any questions about this? Okay, so let me pause here, and all right. Is a unimodular matrix something with a determinant plus minus 1 or plus minus 1 and 0? Now, I was a bit confused because my reference was Papadimitriou and Stiglitz, and that book has been in print for, who knows, 18 years, I don't know, very long time, since 1990. And I was using the second edition, by which time I thought they'd found all their bugs. But in fact, Papadimitriou and Stiglitz is wrong. Okay, it says it defines unimodularity as determinant plus minus 1, but that's wrong. It actually is plus minus 1 and 0. So that's a correction I want to make. So I made the correction in the lecture notes, and I probably should write to Papadimitriou and tell him that there's a bug. Okay, so that's the first thing. And then the second question was about the weighted matching, where we had the situation. I was saying basically that the sum of the sum over w, xuw, equals 1. And some of you came to me and said, oh, wait a minute, you can't do that because, what happens if you have this? You have just 3 nodes here. Well, this guy is not going to have anything, right? So it can't be the case that it's equal to 1. There was a mistake. It really should be less than equal to 1. Right? Obviously, when you have more nodes here or more nodes there, some nodes are going to be unmatched, so that was a bug in the lecture notes as well. So I put up a new version of the lecture notes last night, I think, which has all of these bugs fixed, and somebody else, Francisco, yes, thank you very much. So lots of corrections that you made, so put them all in as well. So it's all there, and so if you keep sending me corrections, I'll put it in. And so the version is as of yesterday, I think. It has at least all the corrections it received so far. The video for the second lecture is also online, and it looks like there's about a 3 to 4 day lag from the time I give the lecture to the time I get it. So I expect Tuesday's video to be available tomorrow, and then I'll put it up. So I'm putting it up as soon as I get it. So it seems to work. I know some of you are watching it. So Usman, I saw you watching it, so I know it works. All right, so I can stop with that now. Thank you. What I'm going to do now is to give you an example of Lagrangian optimization. Hopefully that will make things clearer what's going on. So again, I want to try and come up with an example which is realistic. So let's consider a company, and so there is some company over here, and it has its local intranet, and it has a link to an ISP, an internet service provider. And this is pretty normal. This is how every company connects to the world. They go to an ISP, and they say, okay, I want to get a link. Now, today, most links on the internet, in fact, as far as I know, all links on the internet are typically called all-you-can-eat. So they give you connectivity. They say your capacity is 45 megabits per second, and then we don't care how much data you send. It is what it is. Now, this is changing. Some of you have Rogers, and if you get Rogers, you know today that you have to pay it's a bandwidth cap. You get, I think, 60 gigabytes a month, and if you use more than 60 gigabytes a month, you have to pay more on a per megabyte basis. Also, for those of you who have cell phones and data transfer, you know Rogers, our friend, is going to charge you per byte. If you send SMS, you're paying the equivalent of $20,000 a megabyte, something like that. And both incoming and outgoing for Telus and Bell, but not Rogers. And so you have this notion of paying by the byte. So we're going to have over here, this link is in the future, so they're going to pay by the byte. And this is coming, I'm sure. And so the cost, we're going to say that the cost of a link, oh wait a minute, actually for this one you don't need to pay by the byte, but whatever. Cost of a link is going to be KB, okay? And for our purposes, we'll just say if you send B bytes, you're going to pay KB cost. Now you can also view this as saying if the capacity of this link is B, then you're going to pay KB. It doesn't really matter. Mathematically it kind of boils down to the same thing. So we'll just say cost is KB. And also let's say the mean delay on the link, we'll call that D. Again, you can think of this D as being the time taken for transferring B bytes or the delay on this link overall. Again, it doesn't really matter. The thing that matters is that we often have this kind of relationship, which is BD equals 1. If you increase the link capacity, then the delay goes down. Okay? So I guess I can't. All right, let me take this away. We're not paying by the byte. Sorry. Because if you pay by the byte, when you send more, the delay will go up as well. So ignore that. All right, we're going to restart from again. Rewind to whatever it was. All right. I'm going to do this. I thought I could do it both at the same time, but I was too clever for my own good. So I'm going to do it just one thing at a time. Let's do it simply. So you go to the provider and say, I want to buy a link of capacity B. The provider says, okay, if you buy a link of capacity B, I'm going to charge you KB. All right, fine. And the mean delay on that link is D. And the faster the link you buy, the less delay you have. Okay, so that works out. The other way around, it's a bit messier. I can make it work, but not in real time. All right, so let's just do this. So this is a constraint. This constraint is sort of the laws of physics in some sense. Okay, the higher the capacity. So you can imagine, this kind of works out. If you have a gigabit link, you're basically going to see less delay than if you have a 300 bit per second link. Okay, your mean delays are going to be higher for obvious reasons. So, all right, so we have this, and now we want to know what is the benefit to the user? What is the benefit to the company? Well, let's call the benefit, we'll denote that by U. All right, and that stands for utility. Again, when we do decision theory and game theory, we'll use U all the time, so I just want to bring it up over here. And what we're going to do is to say that the benefit U goes down with delay. So as delay increases, utility decreases, right? And of course, as the cost increases, utility decreases again. All right? And just to make things simple, we'll assume that the relationships are linear. Okay? Now again, we don't have to be linear, but it turns out to be easy to do an example when it's linear. But you can think of, and in fact, all of our stuff will work even if it's quadratic or anything else. Anything polynomial will work fine. But we're just going to keep it linear just to make things simple. So we'll define U to be minus KB minus D. Okay? That's very simple. As the cost goes up, my utility goes down. As my delay goes up, utility goes down. Okay, you can see it's linear. Okay, and so in fact, I could have used this. I could have used linear programming to solve it, but I'm going to use Lagrangian techniques just to illustrate it. Okay, so we have U equals KB minus D, and this is of the form fxy, right? It's basically U of BD, right? Utility of any value BD. So you can think of the plane has two axes, the B axis and the D axis. As we move along the BD plane, we get different values of U. Of course, everything is going to be negative. Okay, U, in fact, is never going to be positive, but that's fine. And we want to, of course, maximize u. We want to find the least negative point. And here the constraint, BD equals 1. This is basically